Okay, thanks a lot for the opportunity for me to have the opportunity to introduce some of our research at Google DeepMind that along the line of multimodal AI research. So I'm a research scientist at Google DeepMind. In the last few years, it has become more and more clear that if we manage to train large models on a large scale and diverse data set, we will usually get a better and better generalization performance. So there have been evidence work in text domain for NLP from OpenAI and from Google. And also we show very strong evidence in the image and audio and the video domains. As we see, when we push the limit of using more and more data and training larger and large data models, compute will become one problem, and data will become another problem. With the exponential growth, or even super exponential growth of the data size, we are already training on all the internet scale text corpus. So what will be the next step when we run out of text? So the multimodal data, beyond the text, such as image, audio, speech, video, and other other modalities of data become a very natural sources for us to look for more training data to feed into even bigger models. So there have been work in the images that we can split image into patches and convert it into tokens. And also there have been a lot of research on audios, consider it as language models, and also videos. So today I would like to talk about the two lines of research that we have done that try to train a generalizable models on multimodal data sets. So text-to-speech has been used in our daily life in personal assistants, in smart speakers, in the translations, and also map navigations. At DeepMind, we developed WaveNet in 2016. That became state-of-art for text-to-speech models by the time. We consider the sequential modeling of the raw waveform samples as a sequence modeling problem where we can train one deep convolutional neural network to model the conditional distribution of the next audio waveform sample value given the previous samples. So that achieved the state-of-art performance in both the negative log likelihood and also when evaluated by human evaluators in terms of the naturalness of the sample quality. However, in order to obtain those kind of state-of-art results for a single voice model, we need tens of hours of training data just for one person. So that's doable for a few voices, but if we want to scale it up and provide a large, diverse library of the voices, or in different languages, it becomes very challenging. So in 2018, we start to think about whether we can develop more data efficient or sample efficient way to adapt the text-to-speech models into individual voices with a lot fewer data. So the idea is that given some text-to-speech model, if we can provide some new audio utterances with maybe only a small amount, instead of hours, tens of hours, we want to provide minutes of audio data, can we adapt TTS system to a new voice? So our approach is actually quite straightforward. We tried quite a few different ways, but what we find what's the most natural or straightforward, also it's working best, is that we can start with pre-training large scale, pre-training a multi-speaker TTS model on a large scale multi-speaker data set. So in this data set, we collected public data sets with hundreds of speakers. And then in our model, we share the main stack of WaveNet neural network. And then for every single speaker, we train a separate embedding vector per person. Then after the pre-training phase, we given a new data set of a new voice, we can just randomly initialize the embedding vector for a new speaker, and then fine-tune the wavenet network. We find that that actually works a lot better than other methods we have tried. And it obtained like the state-of-the-art by the time in the both log likelihood and also the sample quality, also the voice similarity. So how much data do we really need for our adapted TTS system? We take a third party like speaker verification model, where you can measure the similarity between two utterances. And then we compute the similarity score, like given one real utterance from the target person we want to imitate, and another utterance that can be another real utterance from the same speaker, or it can be a synthetic utterance from our model. On the first column, we show that this is the scatter plot of the similarity scores from pairs of real utterances from the same person. And then if we start with the very little little data to adapt our models, we find the similarity score is quite low. But when we start to use more and more data with about 10 seconds of the data to adapt our TTS model, we find it starts to show some similarity of the adapted voice to the target voice. And when we use like up to 10 minutes, the spread of the similarity score is already very, very close to the similarity between two real utterances. So roughly speaking, like with 10 minutes of data, you can get some kind of voice that like adapted voice that's hard to be tell apart by a speaker verification model. So why do we want to develop such kind of like sample efficient kind of adapted TTS? So one of the motivation is that we want to, we collaborated with the Google project Euphonia. So the mission of that team is to use the audio rate, like speech rate techniques at Google to help people with impaired speech. For example, like in this example, we worked with a person called Tim Shaw. He was an NFL football player when he was diagnosed with ALS. So with that disease, like you will gradually lose the control of your muscles, and you become gradually not able to move, not able to stand or speak. So another person with ALS is Stephen Hawking. So we took some interview like videos from Tim Shaw, like he did like a few years ago. Extract the audio and get the transcript and use that to adapt our TTS model to his voice. Now, like with these techniques, he would be able to generate the speech using his original voice again, and this makes actually quite kind of impact to the communication with his family and friends. With the success of this adaptive, like data efficient TTS, we are thinking like whether we can extend this to more data modalities. So instead of generating just audio from text, we're thinking whether we can generate the video, including both the audio and the images like from the text input. So we partnered with the Universal Translator team at Google in the early stages of their project. And then we would like to do this kind of, we call it auto-visual dubbing project, where instead of generating just audio, we also like to generate the videos. So the majority of the videos on YouTube is in English, but the users of the YouTube come from all over the world. When we have so this is an example of the TensorFlow online course given in English. It's accessible to people who knows English, but not to other people of other languages. So our vision is that we want to make the video universally accessible to people speaking in any languages. So what we would like to do ideally is that take a video speaking in any languages. We want to use the auto-translation to translate the script into a different language, then synthesize the speech in the target language using the original voice of the speaker. And also we would like to modify to reanimate the lip movement of the speaker such that when a person in a different language watches this video, this was just like a video in a foreign language, naturally, without the help of any subtitles. So it requires a lot of different techniques. For example, we need to extract the transcript from video. We need to get a clean speech utterances from the background noise and music, then translate the transcript into a target languages, then adapt our voice, the TTS model, to the speaker's voice, but then synthesize that in a foreign language. Then we also want to reanimate the lip movement, then lastly combine all of these outputs into the new video. So in this model, we just look at voice, the two steps. So to synthesize the speech in foreign languages, this is the voice imitation technique we just talked about earlier. And then we also want to extend that to videos to synchronize the lip movement with the generated audio in the foreign language. So the idea is actually very, very, very similar to the audio part. We call it the large-scale multilingual audiovisual translation and dubbing. So we collect, so for the audio part, it's quite similar. Instead of training on English only, now we collect a data set with over 1,000 speakers in different languages. And then we want to train a multi-modal, multi-speaker TTS system. Now with the audio from the original the video, we can quickly adapt that to the voice of the lecturer and then synthesize the audio in for example, in the Spanish language. And then on the top path of the data diagram, we also collect multilingual, multi-speaker audio, the video clips from YouTube, public YouTube videos. Then train a multi-speaker, speaker-independent, actually lip synchronization model that's driven by an audio signal and some reference images of the speaker. We can synthesize the speaker with the lip movement synchronized with audio. Then given a new video, we can quickly fine-tune the model into a single speaker lip sync model. So I'll skip these tech details of the network, but it's based on the UNet and take the input the target audio, some reference, some lip area images of reference from reference images speaking in other utterances. And the input frame is the video we want to reanimate the lip movement with the original lip masked. So one of the main contribution of this project is that we collected a large-scale multilingual audiovisual data set. This is by far, by the time, the largest one that includes over 3,000 hours of the video clips with 3 million utterances and span over 400,000 speakers. What we find is that when we train our multilingual and multi-speaker model on the union of all the different languages, it can perform quite comparably or even better than a model trained on even a single languages. And of course, it becomes a lot better than all the other languages when we evaluate on the holdout multilingual eval data set. So similarly, similar to the audio examples, we find the generalization when we train on a diverse multilingual, multi-speaker data set on the video model. So in this example, I will just show a demo of a lecture that was originally given in Spanish. So this is the original video of talking about TensorFlow.
Hola, bienvenidos a Coding TensorFlow, un programa en el que nos enfocamos en técnicas de programación para machine learning.
And then we use a Google translation to translate the transcript and regenerate the audio and the video in English.
Hello and welcome to Coding TensorFlow, a series of videos where we focus on techniques for coding machine learning and artificial intelligence. I'm Martin.
Yeah, so this was some early demos by the Google Translate, the Universal Translate project. there are some more demos on the YouTube. Like, feel free to check them out. So going beyond the regular like multimodal data for like with images and audio or videos, I'm actually quite excited about a more recent project that we train an agent in the reinforcement learning settings on a lot more kind of multimodality data, including both the audios, visual, text, and also robotic controls and the latent states, etc. It's not just limited to the standard like data modalities. So for reinforcement learning, people have trying to push towards like artificial general intelligence for years. There are different meanings of the general AI. So in 2015, DeepMind developed the DeepQ network that uses a single RL reinforcement learning algorithm that we can train different agent models, one per Atari game, and reach the human level, like human level performance for all the Atari games. And later in the VMPO work, they just, instead of using a single algorithm, they use RL to train a single model that in the multitasking setting. Then the single model with a single set of parameters can play all the 57 Atari games pretty well. And then with the new project, we call it Gato. It's a generalist agent. Then we are able to train a single model for over hundreds of different tasks. So in the previous examples, they trained on the Atari game. It's in the single domain that we share the same input and input like observation space and output action space. But in the Gato project, it can take arbitrary reinforcement learning tasks or text or image understanding tasks, and then output like any like actions or like text or videos in very different data modalities. Oh. Okay. So how do I enlarge it? Let's see. Oh, okay. Thank you. Sorry, I can't play this animation, but this is the one agent that play in hundreds of simulated environments, including Atari games and DM like controls in simulations and also simulated robot arms. We can also use the same agent with the same like set of parameters to do as a chatbot to generate dialogues, or use it to do like image question answering, or use it to control the real robot arms. Okay, so in order to expand that to all different kinds of data format, the main idea is that we would like to serialize all these data into a single flat sequence of tokens. So these tokens can be used to represent images, text, the features of the agent, of the environments or the robots, and also different action spaces like the button pressed in Atari games or other discrete or continuous observations and actions. So we consider every task here as one type of reinforcement learning environment that includes one or multiple interactions with the environment. For example, for the Atari game, it's very natural. We observe some images, we take action, and then observe another image and take action. For text, we can consider the text generation as just one round of interaction to generate some text, or conditional on some prompt, or we can consider it as a multi-round kind of interactions with a chatting bot with a human. Similarly, for the image question answering, we take the input image and the question as the observation to the agent, and then the action the agent can take is to generate a text response. So we serialize all these data into a single sequence that contains like multiple interactions. Every interaction includes the observation and the action taken by the agent. Then we train it just as a language model using a large transformer. So with this training, we are basically so this also called like supervised learning or behavioral cloning. So what we try to do is to train an agent that can do as well as that demonstration given to the model. So more particularly, like for text, we just follow the regular like practice as a language model. So tokenize the text into pieces of tokens and convert it into embedding vectors. For some like latent features, for example, the speed and angle of the cart pole we want to control, we will first discretize the continuous state representations into discrete bins, and then convert it into the embedding vector using a lookup table. So the embedding table is trained together with the main model. Similarly, it's applied to continuous actions, and we convert everything into latent embedding vectors. Every embedding vector corresponds to one token. We also add the relative position encoding to indicate which feature or the input it is in every round. And similarly for image, we take the approach of the vision transformer, split one image into 16 by 16 patches. And then for every patch, we pass it through a ResNet and extract the feature that represents one patch. Then concatenate, put all these patch representations all together in a sequence, together with the action. Now we put everything all together. In every interaction with the environment, we can take the input from images, from text, and then the action taken by the agent. We put all these like different rounds all concatenated together into a single full sequence of tokens. So to train this model, because we want to train an agent that can take actions, we don't really care about what observation we observe. So in that case, we train our agent to predict the action taken by the agent. So for example, in the text generation task, if all the text is the action we want to take by the agent, then we want to train the model to predict every token for the text. But then for the image question answering, because the action is the answer we want to output, we mask all the other tokens and only want to train the model to predict the answer generated by the model. Now, once we train this model, to run it as an agent in the inference time, we will provide, for every interaction, we will provide the previous observations all tokenized, sequentialized into a sequence. Then we draw a sample from the model to generate the action tokens and decode the action into the real actions that can be put to the environment. Then after we take an action, we will observe some new observations, concatenate the new tokenized observation into the sequence, and then sample the action token for the next interaction. So, the majority of time is actually of the project is spent on collecting this diverse and multi-modal data set. We include the tasks from hundreds of simulated control tasks, from the vision and language data sets, and also from the real robot like block stacking tasks. For the simulated controls, it includes the image-based observation space like the Atari and DM Lab, that's a 3D simulated environment. And also the continuous control tasks where we observe the state representations inside of the images. And also we will have some reinforcement learning environment with the text as the input. So given the text, the agent needs to learn to do to take some action in this environment. For vision and text, we include both like single model data set used such as the ImageNet and massive web that contains either the image or text. We also take the paired vision and image data set, paired vision and text data set, such that we can try to learn the alignment between images and the text. We also include the four tasks holdout from the training set, and we use it to test our performance for the auto distribution, the generalization. So how does this model perform once we train it in this multitask setting. This plot shows the performance. So to measure the performance, we look at, so the x-axis shows the threshold of the performance of our agent compared to the percentage of the expert score. So we have the expert demonstrations given for all the different tasks. And then the y-axis shows how many tasks we are able to achieve to go beyond the threshold. For example, for this point, it shows that Gato performs over 450 tasks out of the 604 tasks at an over 50% of the expert score threshold. We also find that with the bigger models, we can achieve usually a better generalization performance across all the tasks. So, now we evaluate. So the previous image shows the performance on the in-distribution tasks, all the tasks we have been trained during training. Now we want to show how it performs on the out-of-distribution task that we hold out from training. Then, given some demonstrations, expert demonstrations, we want to fine-tune the Gato model to individual out-of-distribution tasks. For example, in this cart pole swing task, where we want to keep this the cart pole stand up, then we find that using a single demonstration, expert demonstration can already perform pretty well. And then when we train it, when we fine-tune it, starting from the full trained Gato, it performs better than the Gato model that's trained on the in-domain task only. By in-domain, I mean all these control tasks except this cart pole task. And then again, this green curve is better than the blue curve. That is when we pre-trained the Gato model using text and images, so out-of-domain data, without any data from the control task. Then it can still perform learn something, but not as good as we pre-trained the model using in-domain data. And lastly, this pre-trained model is still better than just training the agent to do cart pole based on the demonstration only from scratch. And then for the RGB, real robot stacking task. So here we want a more robot to stack one block in some color on top of the other. Every block comes into 3 colors, and every block can have different shapes and different sizes. So we train our Gato on different kinds of, all different combinations of the color, shape, and size. Every combination corresponds to one specific task. And we want to show how it performs in some different combination of these triplets that are not present in the training. We find that with a single, so this is in the simulation of the environment. We find that with a single demonstration, it can already perform as well as the behavior cloning agent that's trained from all the demonstrations for this scale generalization task. And then with more demonstrations, it starts to perform better and even matches the expert performance. Because we train our model as kind of behavior cloning, the best we can do is to do as well as the expert. So in this figure, it shows with 100 demonstrations, we can do as well as expert in the simulation. And when we apply Gato to the real robots to make a move, we found that even with a single demonstration, expert demonstration, it can already perform as well as an expert. So here, this orange plot is the bar to train a separate agent using the offline reinforcement learning skill. So with the offline RL, we are able to train better than demonstrations. So we don't want to, we don't really expect the Gato can be as well as this one because we are doing the behavior cloning. But if we apply the reinforcement learning kind of fine-tuning further, we can even improve the Gato and possibly achieve or even outperform the offline RL agent. And lastly, so beyond using it as an agent, we find that when this agent can still do tasks like the chatbot and generate the dialogues with human, and also do the image question answerings. although the performance is not as good as the like single model, like a model transformers designed specifically for question answering or dialogue, but it already shows like pretty good kind of performance in all the other tasks that's jointly trained on. Okay, so as a takeaway message, I think we generally find that when we manage to train the model, a large model on a large scale and diverse data set, it usually show very good generalization performance to auto distribution tasks. And the multimodal data sets have become the source of additional training data beyond text. And we already find like all different kinds of ways to consume the data from multimodalities in the same format as the text, as long as we find a good kind of proper serialization scheme. Yeah, thank you. That's the end of the talk.
Thank you, Yutian. I think we have time for some questions from the audience. Anyone want to ask any questions? Is that on already? Yeah. Yes.
Hi. Thank you. Very nice talk. I have a curious question. Like, we all know that this multi-modal mass scale works much better, but what is the key component to actually keep it work? Like, we know we need a lot of data, but besides that, what is the key component when designing a network? Like, how do you align the deep down information for this multi-modal deep model? Thank you.
I think transformer is just great model. It like when you tokenize the data properly, like for every domain, you probably need a specific way to tokenize the data. But once you get like relatively good like token representations, I think using it, like putting that into a sequence is usually works well. And then what we found really important is to get as much different data, as diverse data as possible. I think we still need to keep the trained data to be close to the test distributions. Yeah, I think transformer plus like more data.
What if we just use many data, like some irrelevant data? Will it hurt the model performance, or do you have to screen the data very well before we actually do the stuff?
Can you repeat your question?
If we dump in many multimodal data, even something not relevant to our task, what happens?
Not relevant, I think. We find that the mixing ratio between different tasks doesn't matter. So we want to use as much data as possible, but if the data is really irrelevant, probably we don't want to give a very big weight during training.
The question can be more in the quality. I think it is not irrelevant and more like noisy or low quality.
Yes, yeah, the quality matters. And also the reason we include text and image, because in the agent we train, we need it to understand images and videos and also text instructions. So if the data is completely irrelevant, like some I don't know, like some like weather forecastings or like business and like intelligent business, like the commercial data, probably it's not useful to train this kind of agent. Yeah.
Let's move on to the next question.
Hi, I'm Yutian, I'm a consultant radiologist and deputy medical director for artificial intelligence for MRAT. Thank you for the presentation. I can already think about use case scenarios in medicine application. I'm just wondering if you had any experience applying multimodal models for medical imaging in particular. And my second question is, every model has an error rate, so if you're introducing multiple models from multiple data set points, is there a chance that we could make things worse? And how do we safety net that? Because when we are making decisions about patient care, we need to make sure that we do no harm first, then think about helping them out.
Yeah, that's a very good question. So for your first question, no, I haven't done project related to medical data. So for the second question, we do like not me actually, but I think there are many literatures about negative transfers. If the data is irrelevant or like with very out of distribution data, then it will do harm for the generalization or transfer to a new task. So I think that's something we do need to be careful with. For images, I feel like, but it's just, I don't know, I don't have a personal experience, but I feel like image data, it's probably more similar to like the control task where you have very different kind of state representations. Like the majority of data is based on images, like if it's CT scan or others. So with proper like domain randomizations, it will be useful for like, improving the generalization.
So we will take 2 more very brief questions, and so then for the rest you can talk offline. Sorry, hi, brief question.
Hi, thank you for your talk. I was wondering how Gato knows what context it's in. Like, for example, right now it's supposed to play an Atari game, or then it's supposed to control a robotic arm. Do you just let it know by text prompt?
That's a good question. I need to check the details. Probably, like I don't remember if we put the task kind of task indicators there, but you can basically tell it from the history. We pass in the multiple kind of interactions. Then the model should be able to tell like which game it is playing.
Right. So yeah.
First, thank you for your presentation. It's very
Just focus on question.
So my question is, I noticed you use transformer to establish the dependency among different modalities, and the attention mechanism is the key mechanism of transformer. And I'm thinking, do you think it is possible to visualize the attention maps of the transformer to do inverse engineering to discovering the underlying physics of the very complex dependency among multi-modal?
Yeah, actually, we do have some demo that shows the attention map. When we do the image, do the robot controls, we can see where it attends to different parts of the robot arms or to the background. So I think, yes, we can do some analysis about understanding about the model, like where the attention is paying attention to different modality of data. I think this is a very active area to research to understand how model interacts with different data. I don't have a direct answer. I think this is very kind of rich places for more research.
Okay, I will take one last question and then move on. Right? So the panels and the speakers for the pitch, please get ready. Right? So, yeah, well, last question.
Thank you. Have you been able to develop any methods that let you, on a per task basis, sort of analyze the contribution of different modalities to that task?
We have some ablation to show when you include different kind of type of data, the performance will be different. Like in these ablations or different source of data, we don't have a per task analysis for the model. That's a very good question. I think there's some research about contribution of single data point. I'm not very familiar with that literature, but I think that's very useful to understand how to find the optimal kind of mixture of tasks to train one generalizable agent.
Well, let's thank the speaker again. Thank you very much.
Thank you.